All right, so we are going to take a look at days 6 and 7 from the 12 days of statistics. So in day 6, you're looking for getting a laying goose on or before the fourth goose. So that would make this a geometric distribution. And so it's binary because either it's a laying goose or not. We can assume independence. We're continuing until we select a laying goose. So first on the 4th, or on or before the 4th. And then we have a fixed probability of success. That's equal to the 0.83. So if we were looking for the probability that it's on or before the 4th, you could set it up with a formula. So that would be on the first trial or the second or the third or the fourth. So for on the first trial, that would just be 0.83. On the second trial, that would mean you fail on the first selection and then are successful on the second. And then we would do something similar until we go to the fourth. So on the fourth trial, that means that we failed on the first 3 and then we're successful on the fourth. Or we can use the geometric CDF here. Your probability is 0.83, and then we're successful on the fourth trial or earlier. So if I were to type that into my calculator, that gives me 0.9992. For the 7th day of Christmas, this time you're looking for exactly 4 out of 7, so that means that this is binomial. And we know that it's binomial if it's that binary because either it drowns or does not. We can assume independence. We have a fixed number of trials, n is equal to 7 here, and a fixed probability of success at 0.23. So to find the probability of exactly 4, if we were using the formula, we'd have the binomial coefficient. We would be looking at 4 choose 7, or I'm sorry, 7 choose 4. Had those backwards. And then probability of success to the 4th power, probability of failure to the third power, because if 4 drown, then 3 do not. Or we can use the calculator. That'd be the binomial PDF here. N is 7, P is 0.23, and then X would be 4. So if I were to type that into my calculator, I get 0.0447. So for section 7.3, we're going to get into the sampling distribution of the sample mean. And so some of the stuff that we're going to see here is similar to what we saw for proportions. The formulas are going to be different. The normality check will be a little bit different, but the rest of the idea is the same. The idea of a sampling distribution is the same. The idea of trying to use z-scores will be the same as we saw in section 7.2. So the first thing that we have here is just looking at the difference between when we use proportions and means, and I think that that's a really important distinction. So I had mentioned this before, we use proportions if we're dealing with categorical variables. If we do quantitative variables, we could use the median, the mean, or standard deviation, but primarily in this course, we end up dealing with the mean. So here we have a estimated population distribution of household incomes on the left. And you can see that that distribution is skewed to the right and is quite variable. And we can also estimate the average, and kind of it's denoted here with the mu being slightly under 100,000, maybe somewhere around $75,000, $80,000. Then over here on the right, we have an estimated sampling distribution. Where we took samples of size 100. So what happened over here on the right is that we would take a sample of size 100 from the population, calculate their average income. Then we take a new sample of size 100, calculate their average income. So then the graph is graphing all of those X bar values. So all of the mean household values are graphed from samples of size 100 over here on the right. So in terms of this estimated sampling distribution, we can see that rather than being skewed to the right, it's roughly symmetric. We can see that it's much less variable when we're looking at those average household incomes than the population distribution. but it is centered around the same value. So this mean over here in the population distribution is pretty close to the mean over here in the sampling distribution. So the rules for the standard deviation and mean for the sampling distribution of sample means is that we have the mean of the sampling distribution equal to the population mean mu, and the standard deviation of the sampling distribution equal to sigma over the square root of n. We do have a couple of conditions here. We still have to have a random sample. The reason, again, for that random sample is for us to then confidently say that our sample statistic is an unbiased estimator for the parameter. It kind of allows us to use this formula for the mean. As far as the standard deviation goes, just as a reminder, if we're sampling without replacement, things are not truly independent. So we need to check to make sure that our sample size is small enough relative to the population size. So this is that 10% condition here. So here we can kind of think of this as our pseudo-independence clause, because when we're sampling without replacement, it's not truly independent. But like we saw in chapter 6, we're saying that if that sample size is small enough relative to the population size, that discrepancy is really not going to make a difference. And we can go ahead and move forward and kind of treat it as independent, even though it's not truly independent. So these two formulas are going to hold true regardless of what the shape of your population distribution is. And we saw that with things like the binomial and geometric distributions in chapter 6. So even if you have a non-normal population distribution, we can still find the average, or what's typical. We can still find the standard deviation, or how far do we expect to deviate from the mean. So here we're looking at a diagram that kind of just combines the idea of a sampling distribution with these rules for the mean. So you have your population over here on the left-hand side. And what we're doing is we're taking repeated samples of the same size from that population, and we're calculating all of those X bar values. When we put all of these X bars together and make our distribution, this is our sampling distribution, for the sample mean. It's centered at the population mean mu, and the variability is sigma over square root of n. So those two formulas that we saw in the previous slide just now represented on a graph. So here, what we need to consider is once we have that mean and the standard deviation, we need to think about under what conditions is it safe for us to calculate z-scores and then use table A or the normal CDF. So here we have the information that we previously saw with the mean and standard deviation, but if your population is normally distributed, your sampling distribution is also going to be normally distributed. It's going to be centered at mu and have a standard deviation of sigma over square root of n. There are also other instances where your sampling distribution will be normally distributed. If you kind of think back to that first slide where you had the population of household incomes that was skewed to the right, but then we took samples of size 100 and that sampling distribution was approximately normal. What we'll learn in the next section of this lesson is that if your sample size is large enough, that will also allow you to have an approximately normal sampling distribution, even if your population is skewed. But we're not quite there yet. For right now, we're just focusing on the case that if our population is normal, the sampling distribution is also going to be normal. So here, we're going to be able to answer a couple of probability questions. They tell us that heights follow a normal distribution. They give us a mean and a standard deviation. So we can use that information to find how likely it is that we randomly select a woman that's taller than 66.5 inches. This is something that we did back in chapter 2. So we already know how to do this, but just to review, we indicate that we have a normal distribution with a given mean and standard deviation from the problem. We can calculate a z-score for this woman. It is always the X bar minus the mean. So just watch the order of subtraction in the numerator. Our z-score is 0.8 here. If you were using the calculator, you would use the normal CDF function. Our lower bound would be 0.8, and our upper bound would be 1 times 10 to the 99th, because we're looking to exceed 66.5 inches. Mean and standard deviation are 0 and 1 once you calculate a z-score. If you're using table A gives you the area to the left, so you would get this 0.7881. We need to subtract from 1 since we want the area to the right. So there's about a 21.19% chance that we randomly select a person that's taller than 66.5 inches. Now, what's new in this section is that we can also consider how likely it is that we select a group of women and their average height exceeds 66.5 inches. So in order to do that, we need the mean and standard deviation for that sampling distribution. So we know that it's random. That's one of our conditions that we have to check. We have the mean of that sampling distribution here at 64.5, and then the standard deviation for that sampling distribution is sigma over the square root of n. We do need to check that 10% condition here because we're sampling without replacement. So we would say something like, it's safe to assume that there's at least 100 women in the population. So that's our second condition that we need to verify. The third condition that we need to verify is just that normality condition. So we would just say something like, since the population distribution is normal, that was given, that means the sampling distribution is also going to be normal. Mean and standard deviation for that sampling distribution is our mu sub x bar and sigma sub x bar. So then we can calculate our z-score. It's our 66.5 minus 64.5 over 0.79. And then again, just like the last one, when we calculate our probability, if we're using the normal CDF, 2.53 would be the lower bound, 1 times 10 to the 99th would be the upper bound, 0 and 1 for the standard deviation and mean and standard deviation in the right order. And then we're looking for the area to the right. So again, if you were using table A, this is the area to the left, subtract from 1. So it's about a 0.6% chance. So it's much more likely for us to select one woman that's taller than 66.5 than a group that has an average of 66.5 or taller. And so one thing that you will start to recognize, or hopefully will start to recognize, is that your sampling distributions are always less variable than the population. So when you're looking at extreme values, so something far from the mean like 66.5, it's going to be more common to see an individual that's that tall than it is to see an average that's that tall. And so here you can kind of see in the picture of the population versus the sampling distribution. Our population distribution is much more spread out. In the middle here, the sampling distribution is much more narrow. And so it's also much taller because these are density curves. The area under the curve has to equal 1. So if we're going to bring in that variability, that means that there are more X bar values closer to the mean. So that's why the height is increased of that sampling distribution. So your assignment are these book problems here, and then we will take a look at 7.3b in class on Monday. And just remember to follow the dates for the assignments that are on this week's work and not the ones that are on Schoology, since our class periods are different because of the cancellation yesterday. And if you have any questions about what's due when, please let me know, but don't worry about things saying late on Schoology because your dates are different from first period.